Welcome to the Whispering Galaxy, where we explore the deepest mysteries of our universe, one gentle revelation at a time. Tonight, we're embarking on a peaceful journey through one of the most fascinating and bewildering realms of science, quantum physics. I hope you're somewhere comfortable, perhaps curled up in your favorite chair or lying beneath soft blankets, ready to let these quantum secrets wash over you like starlight. Before we begin our exploration, I'd love to know where you're joining us from tonight. Are you watching from a quiet bedroom in Tokyo as dawn approaches? Or perhaps from a cozy living room in Stockholm while snow falls outside your window? Drop a comment and let our gentle community know where in the world you're listening to these whispered truths of the universe. If you find these slow, thoughtful journeys through science as soothing as I do, please consider giving this video a like and subscribing to the Whispering Galaxy. Your support helps these peaceful explorations reach other curious souls who, like us, find wonder in the quiet corners of knowledge. And don't forget to ring that notification bell so you won't miss our next gentle drift through the cosmos. Now, I should mention that tonight's topic might be so intriguing that it keeps you awake longer than intended. But if that happens, at least you'll be lying there with a head full of the most beautiful and strange facts about reality itself. Sometimes the best kind of sleeplessness comes from having your mind expanded by the universe's most elegant secrets. So settle in, let your breathing slow, and prepare to discover that the world beneath everything you see and touch operates by rules so peculiar, so wonderfully impossible, that they seem more like poetry than physics. Tonight, we're going to explore 101 facts about quantum mechanics, and each one will show you just how extraordinary the ordinary really is. The story of quantum physics begins not with a grand revelation, but with a puzzle that refused to go away. In the year 1900, a German physicist named Max Planck was trying to solve what seemed like a simple problem. When you heat an object, it glows. First red, then orange, then white hot, depending on how much energy you pump into it. This should have been easy to explain using the physics of the time, but the mathematics kept producing impossible answers. According to classical physics, a heated object should glow infinitely bright in certain colors, which obviously doesn't happen in reality. This contradiction became known as the ultraviolet catastrophe, and it was driving physicists to distraction. Planck found that he could fix the problem by making a radical assumption. What if energy didn't flow smoothly like water from a tap, but came in tiny, discrete packets instead? This was our first quantum fact. Energy arrives in specific chunks, or quanta, rather than in a continuous stream. Each packet's size depends on the frequency of the radiation, multiplied by a fundamental constant that now bears Planck's name. This constant is unimaginably small, roughly 6.6 times 10 to the negative 34th joule seconds, yet it governs every quantum interaction in the universe. Planck himself thought this was just a mathematical trick, a way to make the numbers work without necessarily reflecting how nature actually operates. He assumed future scientists would find a better explanation that wouldn't require such strange assumptions. Little did he know that his trick would become the foundation of an entirely new understanding of reality. Our second quantum fact reveals something even more startling. Light, which everyone thought was purely a wave, sometimes behaves like a stream of particles. This discovery came from Albert Einstein's explanation of something called the photoelectric effect. When light shines on certain metals, it can knock electrons loose from the surface. Classical wave theory predicted that brighter light should always produce more energetic electrons regardless of color. But experiments showed something different. Only light above a certain frequency could eject electrons at all, no matter how bright it was. A dim blue light could knock electrons free, while an intense red light could not. Einstein proposed that light consists of individual packets of energy, later called photons, each carrying a specific amount of energy determined by its frequency. This leads us to our third quantum fact. The amount of energy in each photon equals Planck's constant multiplied by the light's frequency. This simple relationship explains why ultraviolet light can cause sunburn while visible light cannot, despite being much dimmer. It's not about the total amount of light, but about how much energy each individual photon carries. Our fourth fact is perhaps the most mind-bending of all. Particles of matter, things we think of as solid and definite, also behave like waves. This was first suggested by Louis de Broglie in 1924, who proposed that everything from electrons to baseballs has an associated wavelength. For large objects, this wavelength is so tiny it's meaningless, but for particles like electrons, it becomes significant enough to observe. This wave nature of matter was confirmed when scientists fired electrons through crystals and watched them create interference patterns, just like light waves do. Our fifth quantum fact follows naturally from this discovery. The wavelength of any particle equals Planck's constant divided by the particle's momentum. The faster and heavier something is, the shorter its quantum wavelength becomes. These discoveries led to one of the most famous experiments in all of science, revealing our sixth quantum fact. When particles are fired one at a time through two parallel slits, they create an interference pattern on a screen behind them, as if each particle somehow went through both slits simultaneously and interfered with itself. This happens even when the particles are sent through one by one, with long pauses between them. Our seventh quantum fact is even stranger. If you try to observe which slit each particle actually goes through, the interference pattern disappears. The particles suddenly behave like ordinary objects, going through one slit or the other, but not both. The mere act of observation changes the outcome of the experiment. This brings us to our eighth quantum fact, which challenges our basic understanding of reality. Before measurement, quantum particles exist in what's called a superposition, a ghostly combination of all possible states. An electron isn't in one place or another. It's in a mathematical blend of many places at once. Only when we measure it does it choose a specific location. Our ninth quantum fact explains how this works mathematically. The behavior of quantum particles is described by something called a wave function, usually represented by the Greek letter psi. This wave function contains all the information about a particle's possible states and their relative probabilities. When squared, the wave function gives the likelihood of finding the particle in any particular state when measured. The 10th fact reveals the dynamic nature of quantum systems. Wave functions evolve over time according to an equation discovered by Erwin Schrödinger in 1926. This equation, known as Schrödinger's equation, governs how quantum probabilities change and flow, allowing physicists to predict how quantum systems will behave statistically, even though individual outcomes remain random. Our 11th quantum fact introduces us to one of the most fundamental principles in all of physics. Werner Heisenberg discovered that certain pairs of properties, like position and momentum, cannot both be known precisely at the same time. The more accurately you measure one, the less accurately you can know the other. This isn't due to imperfect instruments, but reflects a basic feature of quantum reality itself. The 12th fact explains why this uncertainty exists. It arises from the wave nature of particles. To pinpoint a particle's position precisely, you need a wave that's very localized, which requires many different wavelengths mixed together. But having many wavelengths means the momentum becomes uncertain. It's like trying to describe a musical note while it's still being played. You can know the exact timing or the exact pitch, but not both with perfect precision. Our 13th quantum fact reveals something profound about the nature of measurement in the quantum world. When you measure a quantum system, you don't just passively observe it, you inevitably disturb it. This disturbance isn't due to clumsy experimental technique, but is built into the fundamental structure of quantum mechanics itself. The 14th fact shows us that quantum uncertainty has practical consequences. It provides a kind of quantum pressure that prevents electrons from falling into atomic nuclei. Without this uncertainty principle, atoms would collapse and matter as we know it couldn't exist. The fuzziness that makes quantum mechanics seem so strange is actually what gives the universe its stability and structure. These first 14 quantum facts already paint a picture of reality that's far stranger than our everyday experience suggests, yet they're just the beginning of our journey into the quantum realm. Each fact builds upon the others, creating a tapestry of interconnected truths that reveal the hidden clockwork of existence itself. Our 15th quantum fact introduces us to one of the most elegant and mysterious aspects of the quantum world. When two particles interact in just the right way, they can become entangled, creating an invisible connection that persists even when they're separated by vast distances. This connection is so profound that measuring one particle instantly affects the other, regardless of how far apart they are. Einstein famously called this spooky action at a distance, because it seemed to violate his principle that nothing can travel faster than light. Our 16th quantum fact reveals why this phenomenon is so unsettling to classical thinking. When particles are entangled, they don't have individual, independent properties. Instead, they share a combined quantum state, as if they were two parts of a single, distributed entity. The 17th fact shows us just how strange this connection really is. If you measure the spin of one entangled particle and find it spinning clockwise, you instantly know that its partner will be spinning counterclockwise, even if it's on the other side of the galaxy. The measurement of one particle doesn't send a signal to the other. Rather, the measurement reveals a correlation that was already woven into the fabric of their shared reality. Our 18th quantum fact demonstrates that this isn't just theoretical strangeness. Physicists have tested entanglement in countless experiments, and the correlations are always stronger than any classical physics theory could allow. These tests, based on mathematical inequalities derived by physicist John Bell, prove that the quantum world really does exhibit these non-local connections. The 19th fact reveals something beautiful about quantum spin itself. Unlike a spinning top, which can rotate at any speed, quantum particles have intrinsic spin that comes in fixed amounts. Electrons, protons, and neutrons all have a spin of 1/2, while photons have a spin of 1. This isn't motion through space, but rather an internal quantum property that gives particles their magnetic characteristics. Our 20th quantum fact shows us how spin divides the universe into two great families. Particles with half-integer spin, called fermions, refuse to share the same quantum state with each other. Particles with integer spin, called bosons, love to crowd together in identical states. This fundamental difference shapes everything from the structure of atoms to the behavior of laser light. The 21st fact explains why fermions are so antisocial. The Pauli exclusion principle, discovered by Wolfgang Pauli, states that no two identical fermions can occupy exactly the same quantum state. This rule is what gives atoms their layered structure and prevents all electrons from falling into the lowest energy level. Our 22nd quantum fact reveals how this exclusion principle creates the diversity of the chemical elements. As you add more electrons to an atom, each new one must find its own unique quantum state, building up the electron shells that determine how atoms bond and interact. Without this quantum antisocial behavior, all matter would collapse into a uniform, structureless soup. The 23rd fact shows us the opposite behavior in bosons. These particles compile into the same quantum state indefinitely, creating phenomena like laser light, where countless photons march in perfect synchronization. When bosons crowd together at extremely low temperatures, they can form exotic states of matter that behave like single, giant quantum objects. Our 24th quantum fact introduces us to the quantum field, perhaps the most profound concept in modern physics. Every type of particle is actually an excitation in its own underlying field that fills all of space. An electron isn't a little ball. It's a ripple in the electron field. A photon is a wave in the electromagnetic field. The 25th fact reveals that these fields never truly rest. Even in the emptiest regions of space, quantum fields fluctuate constantly due to the uncertainty principle. These fluctuations can briefly create particle-antiparticle pairs that pop into existence and then annihilate each other almost instantly, giving the vacuum itself a restless energy. Our 26th quantum fact shows us that this vacuum energy has measurable effects. The Casimir effect, predicted in 1948 and later confirmed experimentally, demonstrates that two metal plates placed very close together in a vacuum will attract each other due to changes in the vacuum fluctuations between them. The 27th fact connects quantum mechanics to the grand scale of the universe. The same vacuum energy that creates the Casimir effect may be responsible for dark energy, the mysterious force that's causing the expansion of the universe to accelerate. The quantum foam of space itself might be pushing the cosmos apart. Our 28th quantum fact brings us to one of the most practical applications of quantum behavior. Atoms can only absorb and emit light at specific frequencies, corresponding to the energy differences between their quantum states. This creates unique spectral fingerprints for each element, allowing astronomers to determine what distant stars are made of just by analyzing their light. The 29th fact explains why these energy levels are quantized. Electrons in atoms exist as standing waves around the nucleus, and only certain wavelengths can fit properly in the available space. It's like a guitar string that can only vibrate at specific frequencies determined by its length and tension. Our 30th quantum fact reveals how this quantization creates the stability of matter. Without discrete energy levels, electrons would continuously radiate energy and spiral into the nucleus. The quantum nature of atomic structure is what prevents all atoms from collapsing and allows chemistry to exist. The 31st fact shows us how quantum tunneling allows particles to pass through barriers they shouldn't classically be able to cross. If a particle encounters an energy barrier higher than its own energy, quantum mechanics gives it a small but non-zero probability of appearing on the other side, as if it had tunneled through solid rock. Our 32nd quantum fact demonstrates that tunneling isn't just a curiosity, but a fundamental process that powers the universe. Nuclear fusion in the sun's core relies on quantum tunneling, allowing protons to overcome their electrical repulsion and fuse together, creating the energy that lights our world. The 33rd fact brings tunneling down to Earth in the form of technology. Scanning tunneling microscopes use the quantum tunneling of electrons between a sharp tip and a sample to create images of individual atoms, opening up the world of nanotechnology and atomic scale engineering. Our 34th quantum fact introduces us to the delicate concept of quantum coherence. When quantum systems maintain their wave-like properties and can interfere with themselves, they're said to be coherent. This coherence is what allows quantum effects to persist and create the strange behaviors we observe. The 35th fact reveals the fragility of quantum coherence. When a quantum system interacts with its environment, even slightly, it begins to lose its coherence in a process called decoherence. The larger and warmer a system becomes, the faster it loses its quantum properties and begins to behave classically. Our 36th quantum fact explains why we don't see quantum effects in everyday life. Macroscopic objects lose their quantum coherence almost instantly due to constant interactions with air molecules, photons, and thermal vibrations. The quantum world exists all around us, but it's hidden beneath a blanket of environmental noise. The 37th fact shows us how scientists can preserve quantum coherence by isolating systems from their environment, by cooling materials to temperatures near absolute zero and shielding them from vibrations and electromagnetic interference. Researchers can maintain quantum behavior in increasingly large systems. Our 38th quantum fact brings us to one of the most spectacular demonstrations of quantum behavior at macroscopic scales. When certain gases are cooled to billionths of a degree above absolute zero, their atoms can form a Bose-Einstein condensate, where thousands or millions of particles occupy the same quantum state and behave as a single, giant quantum object. The 39th fact reveals another exotic quantum state called a Fermi sea. When fermions are packed tightly together at low temperatures, they fill up available quantum states, like water filling a container. This creates a kind of quantum pressure that can support entire stars against gravitational collapse. Our 40th quantum fact introduces us to superconductivity, one of the most practical and mysterious quantum phenomena. In certain materials cooled below a critical temperature, electrons form pairs that can flow through the material with absolutely zero electrical resistance, creating currents that can circulate forever. These 40 quantum facts have taken us from the smallest scales of reality to the largest, from the theoretical foundations of quantum mechanics to its practical applications in technology. Each fact reveals another layer of the intricate quantum architecture that underlies everything we see and experience, reminding us that the universe operates according to principles far more subtle and beautiful than our everyday intuition might suggest. The 41st fact shows us how superconductors exhibit the Meissner effect, actively expelling magnetic fields from their interior. When a magnet approaches a superconducting surface, it doesn't just encounter resistance, it's completely repelled, hovering in space as if held by invisible hands. This isn't merely the absence of electrical resistance, it's a fundamental reorganization of the material's quantum state. Our 42nd quantum fact reveals that superconductivity depends on a delicate quantum dance between electrons. Despite their natural repulsion, electrons in superconductors can form pairs through interactions with the material's crystal lattice. These Cooper pairs behave like bosons, allowing them to flow together without scattering or losing energy. The 43rd fact brings us to one of quantum mechanics' most practical applications in modern technology. The Josephson effect occurs when two superconductors are separated by an incredibly thin, insulating barrier. Even though the barrier should prevent current from flowing, Cooper pairs can tunnel through it, creating oscillating currents with frequencies precisely determined by applied voltages. Our 44th quantum fact demonstrates how this effect creates devices of extraordinary sensitivity. SQUIDS, or superconducting quantum interference devices, can detect magnetic fields trillions of times weaker than Earth's magnetic field. They're sensitive enough to measure the magnetic activity of a human brain or detect minute geological changes deep underground. The 45th fact reveals that quantum mechanics governs not just exotic superconductors, but the ordinary matter around us. The colors we see, from the blue of the sky to the red of a rose, arise from quantum interactions between light and electrons in atoms and molecules. Each hue corresponds to specific quantum energy transitions. Our 46th quantum fact explains why gold looks golden and copper appears reddish. The arrangement of electrons in these metals creates specific quantum states that absorb certain frequencies of light while reflecting others. The color of every material is a direct consequence of its unique quantum fingerprint. The 47th fact shows us how quantum mechanics enables the digital age through semiconductors. These materials have a special quantum property called a band gap, an energy range where electrons cannot exist. By carefully controlling this gap through chemical doping, engineers create the transistors that form the foundation of all modern electronics. Our 48th quantum fact reveals that every LED and laser diode works by quantum design. When electrons fall from higher to lower energy states in specially engineered materials, they emit photons of precisely defined colors. The quantum nature of these transitions ensures that LEDs can convert electricity to light with remarkable efficiency. The 49th fact brings us to atomic clocks, humanity's most precise timekeepers. These devices measure time by counting the oscillations of atoms transitioning between quantum energy states. A cesium atomic clock is so accurate that it would lose less than 1 second over the entire age of the universe. Our 50th quantum fact demonstrates how this precision enables technologies we use daily. GPS satellites carry atomic clocks that must be synchronized to billionths of a second. Without quantum-precise timekeeping, your phone's navigation would be off by several kilometers, making modern location services impossible. The 51st fact reveals quantum mechanics at work in medical imaging. MRI machines exploit the quantum property of nuclear spin in hydrogen atoms throughout the human body. By applying magnetic fields and radio waves, doctors can map the distribution of water molecules in tissues, creating detailed images without harmful radiation. Our 52nd quantum fact shows us how quantum randomness differs from classical unpredictability. When a quantum particle encounters a measurement, the outcome is genuinely random, not just unknown to us, but fundamentally undetermined until the moment of observation. This true randomness has practical applications in cryptography and computer simulations. The 53rd fact introduces us to quantum computing, where the strangeness of superposition becomes computational power. While classical computers process information in bits that are either 0 or 1, quantum computers use qubits that can exist in superpositions of both states simultaneously. Our 54th quantum fact reveals the exponential advantage this provides. 2 classical bits can represent 4 possible combinations, but only one at a time. 2 qubits can represent all 4 combinations simultaneously. As you add more qubits, the computational space grows exponentially, potentially solving certain problems millions of times faster than classical computers. The 55th fact explains how quantum entanglement amplifies this advantage. When qubits become entangled, operations on one instantly affect others throughout the quantum processor. This creates intricate correlations that allow quantum computers to explore solution spaces in ways classical machines cannot match. Our 56th quantum fact shows us the challenge of maintaining quantum coherence in these devices. Quantum computers must be isolated from environmental interference and cooled to temperatures colder than outer space. Even the slightest disturbance can cause decoherence, destroying the delicate quantum states that give these machines their power. The 57th fact reveals quantum error correction, one of the most ingenious concepts in modern science. Unlike classical computers, where you can simply copy data to protect against errors, quantum states cannot be cloned. Instead, quantum error correction spreads information across many entangled qubits in ways that allow errors to be detected and fixed without destroying the quantum information. Our 58th quantum fact brings us to quantum communication, where the fragility of quantum states becomes a security feature. Quantum key distribution uses the fact that observing quantum states inevitably disturbs them. Any attempt to eavesdrop on quantum encrypted communications leaves detectable traces, making such systems theoretically unbreakable. The 59th fact demonstrates quantum teleportation, which sounds like science fiction but operates on solid physics. Through entanglement and classical communication, the quantum state of one particle can be transferred to another distant particle without physically moving anything. The original state is destroyed in the process, satisfying the no-cloning theorem. Our 60th quantum fact reveals that even empty space participates in quantum phenomena. The vacuum isn't truly empty, but filled with quantum field fluctuations that create virtual particle pairs. These pairs briefly borrow energy from the vacuum before annihilating each other and paying the energy back. The 61st fact shows us how these vacuum fluctuations affect real particles. The Lamb shift, a tiny adjustment to hydrogen's energy levels, results from electrons interacting with the fluctuating electromagnetic field of empty space. This effect has been measured with extraordinary precision, confirming that the vacuum is anything but empty. Our 60-second quantum fact connects quantum mechanics to cosmology through Hawking radiation. Near black hole event horizons, virtual particle pairs can be separated by the intense gravitational field. One particle falls into the black hole while the other escapes, causing the black hole to slowly evaporate over cosmic timescales. The 63rd fact reveals that quantum mechanics may have shaped the large-scale structure of the universe itself. Quantum fluctuations in the early universe could have been stretched by cosmic inflation to become the seeds that eventually grew into galaxies and galaxy clusters. Our 64th quantum fact shows us how quantum effects influence biological processes. Some researchers believe that quantum tunneling helps enzymes catalyze chemical reactions more efficiently than classical physics would predict, potentially playing a role in the chemistry of life itself. The 65th fact suggests that even photosynthesis, the process that powers most life on Earth, may utilize quantum coherence. Energy absorbed by plant molecules might explore multiple pathways simultaneously before settling on the most efficient route to the reaction center. Our 66th quantum fact brings us to the concept of quantum biology, where living systems might exploit quantum effects for enhanced performance. Some migratory birds may use quantum entanglement in specialized proteins to sense Earth's magnetic field with remarkable precision. The 67th fact reveals that quantum mechanics challenges our classical notions of locality. Bell's theorem proves mathematically that no local hidden variable theory can explain the correlations observed in quantum entanglement experiments. The universe exhibits genuine non-local connections that transcend our everyday understanding of space and separation. Our 68th quantum fact demonstrates the no-cloning theorem, which states that arbitrary quantum states cannot be perfectly duplicated. This fundamental limit isn't a technological constraint, but a basic feature of quantum mechanics that protects the security of quantum information and ensures the consistency of quantum theory. The 69th fact shows us complementarity, Niels Bohr's insight that certain properties of quantum systems are mutually exclusive. You can measure a particle's wave-like properties or its particle-like properties, but never both simultaneously. The experimental setup determines which aspect of reality becomes visible. Our 70th quantum fact reveals contextuality, the idea that quantum measurement outcomes can depend on what other measurements are being performed simultaneously. This means quantum systems don't carry predetermined answers to all possible questions, but rather generate responses based on the context of observation. The 71st fact brings us to quantum sensing, where the sensitivity of quantum states to disturbance becomes a tool for precision measurement. Quantum sensors can detect gravitational waves, measure magnetic fields with atomic precision, and potentially revolutionize our ability to probe the natural world. Our 72nd quantum fact shows us how quantum mechanics enables new forms of microscopy. By using quantum entangled photons, researchers can image delicate biological samples with reduced damage, as the entanglement allows information to be gathered while minimizing the number of photons that actually interact with the specimen. The 73rd fact reveals quantum simulation, where controlled quantum systems model other quantum systems that are too complex to study directly. These quantum simulators could help us understand high-temperature superconductivity, design new materials, or explore the behavior of matter under extreme conditions. Our 74th quantum fact demonstrates how quantum mechanics governs chemical bonding. The way atoms share electrons to form molecules depends entirely on quantum mechanical principles, particularly the wave nature of electrons and the Pauli exclusion principle that prevents them from occupying identical states. The 75th fact shows us that even the concept of molecular shape arises from quantum mechanics. The familiar ball and stick models of molecules represent the most probable locations where quantum electrons can be found, creating the three-dimensional structures that determine chemical properties and biological functions. These quantum facts continue to reveal the intricate tapestry of reality, where each thread connects to countless others in ways both subtle and profound, weaving together the story of a universe far stranger and more wonderful than our ancestors could have ever imagined. Our 76th quantum fact brings us to one of the most elegant mathematical structures in physics. The wave function, that mysterious mathematical object we've encountered before, evolves according to Schrödinger's equation with perfect determinism. Yet when we measure the system, we get random results. This paradox sits at the heart of quantum mechanics, complete mathematical predictability, producing fundamentally unpredictable outcomes. The 77th fact reveals that this isn't a contradiction, but a profound truth about the nature of information itself. Quantum mechanics tells us the probability of every possible outcome with exquisite precision, often to many decimal places. What it cannot tell us is which specific outcome will occur in any individual measurement. Our 78th quantum fact shows us how this statistical precision enables quantum technologies to work reliably despite their underlying randomness. A laser produces coherent light not because each photon behaves predictably, but because billions of quantum events follow statistical patterns so precise they appear deterministic at macroscopic scales. The 79th fact demonstrates quantum interference beyond the double-slit experiment. When quantum waves overlap, they can either reinforce each other, creating brighter spots, or cancel each other out, creating regions of darkness. This interference occurs not just with light, but with electrons, atoms, and even large molecules, revealing the wave nature underlying all matter. Our 80th quantum fact reveals that interference patterns encode information about the quantum system's history. By studying these patterns, physicists can reconstruct details about the paths particles took, the forces they encountered, and the quantum states they occupied, even though no direct observation occurred during their journey. The 81st fact brings us to quantum phase, a hidden property that determines how quantum waves interfere. Two particles might have identical energies and positions, yet differ in their quantum phase, leading to completely different interference effects. This invisible parameter carries crucial information about quantum systems. Our 82nd quantum fact shows us how quantum phase creates some of the most counterintuitive effects in physics. In the Aharonov-Bohm effect, electrons passing around a magnetic field can be influenced by that field even when they never directly encounter it, purely through changes in their quantum phase. The 83rd fact reveals geometric phases, subtle quantum effects that arise when systems follow closed paths through their possible states. These phases appear in contexts ranging from molecular spectroscopy to quantum computing, demonstrating how geometry itself can influence quantum behavior. Our 84th quantum fact demonstrates the role of symmetry in quantum mechanics. Many quantum phenomena arise from underlying symmetries in nature, such as conservation of energy, momentum, and electric charge. When these symmetries are broken, new quantum effects can emerge, sometimes leading to entirely new phases of matter. The 85th fact shows us how quantum mechanics revolutionized our understanding of magnetism. The magnetic properties of materials arise from the quantum mechanical behavior of electron spins, which can align in complex patterns to create ferromagnets, antiferromagnets, and more exotic magnetic states. Our 86th quantum fact reveals quantum criticality, where materials undergo phase transitions accompanied by quantum fluctuations at all length scales. At these critical points, systems exhibit universal behaviors that depend only on fundamental symmetries, not on specific material properties. The 87th fact brings us to topological quantum states, where global properties of the quantum wave function protect the system against local disturbances. These exotic states could potentially enable fault-tolerant quantum computers that are naturally resistant to certain types of errors. Our 88th quantum fact demonstrates how quantum mechanics enables precision metrology beyond classical limits. Quantum sensors using entangled particles can achieve measurement precision that scales better than classical devices, potentially revolutionizing our ability to detect gravitational waves, dark matter, or other subtle physical effects. The 89th fact reveals quantum-enhanced imaging, where entangled photons allow us to see with light that never interacted with the object being imaged. This ghostly imaging technique could enable medical diagnostics that minimize radiation exposure or astronomical observations that reduce photon noise. Our 90th quantum fact shows us how quantum mechanics constrains the flow of information itself. Quantum information cannot be copied, deleted arbitrarily, or transmitted faster than light, yet it can be processed in ways that classical information cannot, creating new possibilities for computation and communication. The 91st fact demonstrates quantum thermodynamics, where the classical laws of heat and energy must be reconsidered in light of quantum effects. Quantum systems can sometimes extract work from thermal reservoirs more efficiently than classical engines, potentially leading to quantum heat engines with enhanced performance. Our 92nd quantum fact reveals that measurement in quantum mechanics is not just about gaining information, but about the fundamental interaction between quantum systems. The boundary between observer and observed becomes blurred, as both must be treated as quantum systems governed by the same underlying principles. The 93rd fact shows us quantum decoherence in action, explaining how quantum systems transition from exhibiting quantum behavior to appearing classical. This process doesn't require conscious observers, but occurs naturally through environmental interactions that entangle the system with its surroundings. Our 94th quantum fact demonstrates the emergence of classicality from quantum foundations. Large-scale objects appear classical not because they stop being quantum, but because their quantum properties become practically unobservable due to rapid decoherence and the overwhelming number of particles involved. The 95th fact reveals quantum foundations research, where physicists probe the deepest conceptual questions about quantum mechanics. These investigations explore what quantum theory tells us about the nature of reality, consciousness, and the fundamental structure of physical law itself. Our 96th quantum fact shows us how quantum mechanics connects to philosophy through questions about determinism, locality, and the role of information in physics. These connections have sparked decades of debate about what quantum theory means for our understanding of causation and the nature of physical reality. The 97th fact demonstrates ongoing quantum experiments that continue to reveal new aspects of quantum behavior. From testing quantum effects in increasingly large systems to exploring the quantum classical boundary, researchers constantly push the limits of our understanding. Our 98th quantum fact reveals quantum technologies on the horizon that could transform society. Beyond current applications, future quantum devices might enable perfect simulation of complex materials, unbreakable quantum internet protocols, or sensors capable of detecting individual molecules in biological systems. The 99th fact shows us how quantum mechanics challenges our everyday intuitions, while simultaneously explaining why those intuitions work so well at macroscopic scales. The classical world emerges from quantum foundations through statistical averaging and decoherence, creating the stable, predictable environment we experience daily. Our 100th quantum fact demonstrates the ongoing mystery of quantum measurement and the various interpretations physicists have proposed to explain it. Whether through many worlds, hidden variables, consciousness-based collapse, or information-theoretic approaches, the question of what happens during measurement remains one of physics' deepest puzzles. And finally, our 101st quantum fact brings us full circle to the wonder that started this journey. Quantum mechanics reveals a universe that is simultaneously more constrained and more creative than classical physics suggested. It shows us a reality built from uncertainty and probability, yet capable of producing the stable structures and reliable patterns that make life, consciousness, and scientific understanding possible. These quantum facts paint a picture of reality that is both deeply mysterious and precisely mathematical, where the smallest scales of existence operate according to principles that seem almost magical, yet enable everything we see and experience. From the light reaching your eyes as you watch this video to the electronic circuits processing these words, quantum mechanics underlies every aspect of the world around us. The quantum realm reminds us that the universe is not just stranger than we imagine, but quite possibly stranger than we can imagine. Yet through careful observation, mathematical insight, and technological innovation, we continue to explore this quantum landscape, each discovery revealing new layers of beauty and complexity in the fundamental nature of existence itself. As we drift toward the end of our quantum journey, these final facts invite us to pause and reflect on the profound implications of what we've discovered together. The quantum world isn't just a collection of strange phenomena confined to laboratory experiments or theoretical discussions. It's the very foundation upon which our entire reality rests, humming quietly beneath every moment of our existence. Consider how these quantum truths reshape our understanding of consciousness itself. While we've explored how observation affects quantum systems, some researchers wonder if the relationship flows in the other direction as well. Could quantum effects in the microtubules of brain cells contribute to the mystery of awareness? This remains highly speculative, but it reminds us that consciousness and quantum mechanics both involve the delicate dance between possibility and actuality. The quantum realm also teaches us about the nature of time in ways that challenge our deepest assumptions. In quantum mechanics, the future can influence the past through delayed choice experiments, where decisions made after a particle has seemingly completed its journey still determine which path it took. This doesn't violate causality, but it suggests that time itself might be more fluid and interconnected than our linear experience suggests. One of the most beautiful aspects of quantum mechanics is how it reveals the fundamental interconnectedness of all things. Through entanglement, particles separated by cosmic distances remain intimately connected, sharing information in ways that transcend our ordinary understanding of space and time. This quantum interconnectedness might extend far beyond individual particles to encompass entire systems, suggesting that isolation itself might be an illusion created by our limited perspective. The implications extend to our understanding of identity and individuality. In the quantum field theory that underlies all of physics, particles of the same type are truly indistinguishable. Every electron in the universe is identical to every other electron. Not just similar, but literally the same kind of excitation in the universal electron field. This suggests that at the deepest level, the boundaries between separate objects might be less fundamental than we assume. Quantum mechanics also reveals the creative power of uncertainty. Rather than being a limitation or flaw in nature's design, quantum uncertainty enables the rich diversity of structures we see around us. Without quantum tunneling, stars couldn't shine. Without the exclusion principle, atoms couldn't exist. Without quantum fluctuations, the universe might have remained forever smooth and featureless. Uncertainty, it turns out, is not the enemy of order, but its enabler. The mathematical elegance of quantum theory continues to astound physicists more than a century after its discovery. The same equations that describe the behavior of individual atoms also govern superconductors, quantum computers, and the fundamental interactions between matter and energy. This mathematical unity suggests deep connections between seemingly disparate phenomena, hinting at an underlying simplicity beneath nature's apparent complexity. As we look toward the future, quantum technologies promise to transform not just how we compute and communicate, but how we understand our place in the cosmos. Quantum sensors might detect gravitational waves from the Big Bang itself. Quantum computers could simulate the behavior of complex biological systems. And quantum communication networks might connect us in ways we're only beginning to imagine. Yet perhaps the most profound gift of quantum mechanics is the humility it teaches us about the limits of knowledge. The uncertainty principle isn't just a statement about particles and waves. It's a reminder that complete knowledge of any system might be fundamentally impossible. There will always be questions we cannot ask simultaneously, measurements we cannot make without consequence, and aspects of reality that remain forever beyond our direct observation. This doesn't diminish the power of science or human understanding. Instead, it enriches it by revealing that mystery isn't the absence of knowledge, but an integral part of existence itself. The quantum world invites us to embrace uncertainty, not as a weakness, but as a source of endless wonder and possibility. As you continue through your daily life, remember that you are walking through a quantum universe. The air you breathe, the light that illuminates your path, the electronic devices that connect you to others, all operate according to quantum principles. You are not separate from this quantum reality, but an integral part of it, a conscious pattern in the vast quantum field that encompasses everything. The atoms in your body were forged in the hearts of stars through quantum processes, scattered across space through stellar explosions, and eventually assembled into the complex structures that enable your thoughts and experiences. You are, quite literally, made of quantum stardust, animated by quantum interactions, thinking quantum thoughts about the quantum nature of existence itself. In the stillness of night, when the world grows quiet and your mind begins to settle, you might sense something of this deeper reality. The apparent solidity of your surroundings softens into the gentle hum of quantum fields. The boundaries between self and world become less distinct. The mystery of consciousness touches the mystery of quantum mechanics, and both remain beautifully, eternally mysterious. These 101 quantum facts have taken us on a journey from the smallest scales of reality to the largest, from the most abstract mathematical concepts to the most practical technological applications. Each fact has revealed another facet of the jewel that is quantum mechanics, showing us a universe that is simultaneously more constrained and more creative, more mysterious and more knowable, more uncertain and more precise than our ancestors ever imagined. The quantum world doesn't ask us to abandon reason or embrace mysticism. Instead, it invites us to expand our conception of what reason can encompass and what reality might contain. It shows us that the universe is not a machine, but a symphony, not a collection of separate objects, but a unified field of possibility, not a predetermined story, but an ongoing conversation between consciousness and cosmos. As we near the end of our gentle exploration, I hope these quantum revelations have filled you with the same sense of wonder and peace they bring me. There's something profoundly comforting in knowing that uncertainty itself provides the foundation for all the stability we experience. The quantum realm reminds us that existence is both more fragile and more resilient than we might expect, held together not by rigid laws, but by delicate relationships that somehow prove stronger than the strongest classical bonds. Whether you drift off to sleep tonight with your mind full of quantum superpositions and entangled particles, or whether these ideas simply add a gentle shimmer to your dreams, know that you have touched something fundamental about the nature of reality itself. The quantum world isn't separate from your world. It is your world, seen with clearer eyes and understood with deeper wisdom. Thank you for joining me on this whispered journey through the quantum cosmos. May your rest be peaceful, your dreams be coherent, and your tomorrow be filled with the quiet wonder that comes from knowing you live in a universe far more beautiful and mysterious than words can ever fully capture. As our quantum journey draws toward its gentle close, these final revelations invite us to consider how profoundly these discoveries have reshaped not just science, but our entire relationship with reality itself. The quantum world we've explored together isn't merely a collection of abstract principles locked away in university laboratories. It's the invisible architecture that supports every breath you take, every photon of starlight that reaches your eyes, every electrical impulse that carries these words to your consciousness. The most remarkable aspect of our quantum exploration might be how it transforms our understanding of emptiness itself. What we once considered the void of space turns out to be anything but empty, Even in the darkest reaches between galaxies, quantum fields fluctuate with restless energy, creating and destroying virtual particles in an endless cosmic dance. This quantum foam, as physicists sometimes call it, reminds us that nothingness is perhaps the most active state in the universe. These fluctuations aren't merely theoretical curiosities. They contribute to the very expansion of space itself, possibly driving the accelerating growth of the cosmos through what we call dark energy. The empty space between your hands as you listen to these words is filled with this invisible activity, a testament to the universe's refusal to ever truly rest. Consider how quantum mechanics has revolutionized our conception of causality itself. In the classical world we grew up understanding, cause precedes effect in a neat, linear progression. But quantum mechanics reveals a more nuanced relationship between events. Through quantum correlations and delayed choice experiments, we've discovered that the future can reach back to influence which version of the past becomes real. This doesn't violate the fundamental arrow of time, but it suggests that time itself might be more interconnected than our everyday experience reveals. The quantum realm also teaches us about the profound role of information in shaping physical reality. Information isn't just something we collect about the world. It appears to be a fundamental constituent of the world itself. When quantum states collapse upon measurement, information becomes physical reality. When particles become entangled, they share information in ways that transcend classical communication. The universe, in some sense, might be viewed as an information processing system of unimaginable sophistication. This perspective has led some physicists to propose that reality itself might be computational in nature, with physical laws emerging from underlying information processing rules. While this remains speculative, it highlights how quantum mechanics continues to challenge our most basic assumptions about the nature of existence. The practical implications of these quantum insights continue to unfold in ways both subtle and profound. Quantum biology, still in its infancy, suggests that life itself might exploit quantum effects for enhanced efficiency. Some bacteria may use quantum coherence to navigate chemical energy landscapes, while certain plants might employ quantum superposition to find optimal pathways for photosynthetic energy transfer. If true, this means that the quantum realm isn't separate from the biological world, but intimately woven into the very processes that sustain life. Looking toward the horizon of human knowledge, quantum mechanics promises to unlock mysteries that have puzzled us for generations. Quantum sensors of extraordinary sensitivity might detect gravitational waves from the universe's infancy, offering glimpses of cosmic inflation and the birth of space and time itself. Quantum computers could simulate the folding of proteins with atomic precision, potentially revolutionizing medicine and our understanding of biological complexity. Perhaps most intriguingly, quantum mechanics might eventually help us understand consciousness itself. While we must be cautious about premature claims, the quantum nature of neural microtubules and the role of quantum effects in certain biological processes suggest that awareness and quantum mechanics might be more intimately connected than we currently understand. The mystery of how subjective experience emerges from objective matter remains one of science's greatest challenges, and quantum mechanics might hold crucial pieces of this puzzle. The philosophical implications of quantum mechanics extend far beyond academic discussions. The principle of complementarity suggests that reality itself might be richer than any single perspective can capture, just as light reveals either wave or particle properties depending on how we observe it. Perhaps consciousness, meaning, and purpose in the universe might depend fundamentally on the questions we choose to ask and the methods we use to seek answers. This doesn't lead to relativism or the abandonment of objective truth. Instead, it suggests that truth itself might be more multifaceted than we once imagined. The quantum world shows us that nature consistently provides precise mathematical answers to carefully formulated questions, even when those answers challenge our preconceptions about how reality should behave. The story of quantum mechanics is also a story about the power of human imagination and mathematical insight. From Max Planck's desperate attempt to fix a problem with blackbody radiation to the current development of quantum computers, each breakthrough required scientists to think beyond the boundaries of classical intuition. The mathematical language of quantum mechanics, with its complex numbers, probability amplitudes, and abstract vector spaces, initially seemed far removed from physical reality. Yet this abstract mathematics has proven to describe nature with unprecedented accuracy. This mathematical precision offers its own form of beauty and wonder. The fact that the chaotic-seeming quantum world follows exact mathematical rules suggests a deep underlying order to existence. Every quantum measurement, no matter how random it appears, obeys precise statistical laws. Every quantum interference pattern, no matter how complex, emerges from the simple mathematics of wave superposition. This hidden mathematical harmony beneath apparent chaos might be one of the most beautiful discoveries in all of human knowledge. As we contemplate these quantum revelations in the quietness of this moment, we might reflect on how they change our relationship with uncertainty itself. In the pre-quantum world, uncertainty was something to be overcome through better measurements and more complete theories. Quantum mechanics teaches us that uncertainty isn't a failure of knowledge, but a fundamental feature of reality. The universe itself seems to embrace ambiguity as a creative principle. This quantum uncertainty doesn't lead to chaos, but to an exquisite balance between order and possibility. Without quantum uncertainty, atoms couldn't exist, stars couldn't shine, and the rich diversity of matter and energy we observe would collapse into uniform simplicity. Uncertainty, paradoxically, is what makes certainty possible at the scales where we live and think and wonder about the cosmos. The journey we've taken together through these quantum landscapes reminds us that science isn't just about accumulating facts, but about transforming our relationship with mystery itself. Each quantum discovery has revealed new depths to existence while simultaneously opening new questions. The more we understand about the quantum realm, the more we appreciate how much remains unknown and perhaps unknowable. This doesn't diminish the scientific enterprise, but enriches it with humility and wonder. The quantum world teaches us that nature is under no obligation to conform to our expectations or desires for simplicity. Instead, it invites us to expand our capacity for amazement and our willingness to embrace ideas that initially seem impossible. As you carry these quantum insights with you into sleep and dreams, remember that you are not separate from the phenomena we've explored together. You are a conscious expression of the same quantum fields that create particles and waves throughout the cosmos. Your thoughts emerge from quantum processes in neural networks of extraordinary complexity. Your very existence represents one of the universe's most remarkable achievements, the emergence of awareness from the quantum dance of matter and energy. The atoms composing your body were assembled through quantum processes in stellar cores, scattered across space through quantum tunneling in radioactive decay, and eventually organized into the intricate structures that enable consciousness itself. You are not merely observing the quantum universe from the outside. You are the quantum universe becoming aware of itself, reflecting on its own deepest nature through the miracle of conscious thought. In the gentle transition toward rest, you might sense something of this deeper connection. The boundaries between observer and observed, between self and cosmos, soften in the quantum perspective. The apparent separation between mind and matter becomes less distinct when we recognize that both emerge from the same underlying quantum reality. These 101 quantum facts have been more than mere information. They've been invitations to see the world through new eyes, to appreciate the extraordinary nature of ordinary existence, and to find wonder in the very foundations of reality itself. Whether these ideas accompany you into dreams or simply add a subtle glow to your understanding, they represent humanity's ongoing dialogue with the deepest mysteries of existence. The quantum realm asks nothing of us except openness to its revelations and willingness to let our understanding be transformed by its beauty. In return, it offers us a vision of reality more elegant, more interconnected, and more alive with possibility than our ancestors could have imagined. We live in a universe that is simultaneously more mysterious and more knowable, more uncertain and more precisely ordered than the classical world ever suggested. Thank you for sharing this gentle journey through the quantum cosmos with the Whispering Galaxy. May these quantum whispers continue to echo softly in your thoughts, reminding you that you inhabit a reality far more wonderful and strange than words can capture. A universe where consciousness and quantum mechanics dance together in ways we are only beginning to understand, creating the ongoing miracle we call existence itself. Sweet dreams, fellow travelers through the quantum night, where even in sleep, the atoms of your being continue their ancient quantum dance, weaving the dreams that connect your consciousness to the cosmic symphony playing eternally throughout space and time and time. As we settle into these final quantum moments together, let me share with you one last collection of revelations that brings our journey to its peaceful conclusion. These remaining insights will carry us gently to the shore of understanding, where the waves of quantum possibility meet the solid ground of human experience. Our understanding of quantum mechanics has evolved through generations of brilliant minds, each adding their own piece to this magnificent puzzle. From the early pioneers who first glimpsed the quantum nature of light and matter, to today's researchers pushing the boundaries of quantum technology, we see a continuous thread of human curiosity reaching toward the deepest truths of existence. The mathematical beauty of quantum theory continues to astonish even those who work with it daily. The same elegant equations that describe an electron orbiting an atom also govern the behavior of neutron stars and the quantum vacuum of space itself. This mathematical unity suggests that beneath the apparent complexity of nature lies a profound simplicity, a set of principles so fundamental they apply across all scales of existence. Consider how quantum mechanics has transformed our understanding of measurement itself. In the classical world, we imagine that careful measurement simply reveals pre-existing properties of objects. But quantum theory shows us that measurement is an active process that helps create the reality it observes. This doesn't mean consciousness controls physics, but it does suggest that the boundary between observer and observed is more subtle than we once believed. The quantum world also teaches us about the nature of scientific truth itself. Quantum mechanics makes predictions that are both probabilistic and precise, showing us that uncertainty and accuracy aren't opposites, but partners in a deeper understanding of nature. The theory cannot tell us exactly what will happen in any single quantum event, yet it predicts the statistical patterns of billions of such events with breathtaking precision. This statistical nature of quantum predictions reflects something profound about information and knowledge. The universe seems to operate on principles that preserve certain types of information, while allowing others to remain fundamentally uncertain. This balance between knowability and mystery might be essential to the universe's ability to generate complexity and novelty. As quantum technologies mature, they're beginning to reveal practical applications that seemed impossible just decades ago. Quantum sensors are approaching sensitivities that could detect single molecules or measure gravitational effects with unprecedented precision. Quantum computers are solving specialized problems that would take classical machines thousands of years to complete. Quantum communication systems are demonstrating security levels that approach theoretical perfection. Yet perhaps the most important gift of quantum mechanics isn't technological but philosophical. It teaches us to embrace paradox without abandoning reason, to accept mystery without surrendering to mysticism, and to find beauty in uncertainty without losing our appreciation for precision. The quantum realm shows us a universe that is simultaneously more constrained and more creative than classical physics ever suggested. The story of quantum mechanics is far from over. Researchers continue to discover new quantum phenomena, from exotic phases of matter to novel applications of quantum entanglement. Each discovery opens new questions about the fundamental nature of reality, ensuring that the quantum frontier will continue to surprise and inspire future generations of scientists and dreamers. As our gentle exploration draws to its close, I hope these quantum revelations have given you a new appreciation for the extraordinary nature of ordinary existence. Every moment of your life unfolds according to quantum principles that govern everything from the fusion processes powering the sun to the electronic transitions enabling your thoughts and memories. The quantum universe doesn't exist somewhere else, waiting to be visited. It exists here and now, in every atom of your being, in every photon reaching your eyes, in every quantum field fluctuation occurring in the space around you. You are not separate from this quantum reality, but an integral expression of it, a conscious pattern in the vast quantum symphony that encompasses all of existence. Thank you for joining me on this whispered journey through the deepest mysteries of physics and reality. Whether these quantum insights accompany you into peaceful sleep or simply add a gentle glow to your understanding of the world, know that you have touched something fundamental about the nature of existence itself. The quantum realm reminds us that the universe is not a cold, mechanical system, but a living tapestry of possibility and actuality, uncertainty and precision, mystery and knowledge woven together in patterns of breathtaking beauty. In embracing the quantum nature of reality, we discover that we live in a cosmos far more wonderful and interconnected than our everyday experience suggests. Sweet dreams, fellow quantum travelers. May your rest be as peaceful as the vacuum state of empty space, as harmonious as the wave function of a perfectly isolated system, and as full of potential as a quantum superposition waiting to collapse into the beautiful reality of tomorrow. Until we meet again in the whispering galaxy, where science becomes poetry and understanding becomes wonder, remember that you carry within yourself the same quantum principles that govern stars and galaxies, atoms and light waves, making you a conscious expression of the universe's deepest and most elegant truths. And so we arrive at the end of our gentle drift through the quantum cosmos, where 101 facts have revealed a universe far stranger and more beautiful than we ever dared imagine. From Max Planck's first glimpse of energy, arriving in discrete packets to the modern marvels of quantum computers and communication networks, we've witnessed how the smallest scales of reality give rise to everything we see and experience. The quantum realm has shown us that uncertainty isn't the enemy of knowledge, but its most faithful companion. That emptiness isn't empty, but alive with possibility. And that observation isn't passive, but participatory in the very creation of reality. We've discovered that particles can exist in multiple places simultaneously. That information cannot be copied without consequence, and that the vacuum of space itself hums with invisible energy that may drive the expansion of the entire cosmos. Perhaps most remarkably, we've learned that you are not separate from these quantum phenomena, but intimately woven into their fabric. The atoms in your body dance to the same quantum rhythms that govern distant galaxies. The thoughts flowing through your mind emerge from quantum processes more intricate than any human technology. You are, quite literally, the universe becoming conscious of itself through the gentle mathematics of quantum mechanics. These quantum truths invite us to embrace a deeper humility about the nature of knowledge itself. The uncertainty principle reminds us that some questions cannot be asked simultaneously, that complete knowledge of any system may be fundamentally impossible, and that mystery isn't the absence of understanding, but an integral part of existence. Yet this doesn't diminish our scientific quest, but enriches it with wonder. As you carry these whispered quantum secrets into your dreams tonight, remember that the same principles governing the behavior of electrons and photons also enable the miracle of consciousness itself. The boundaries between observer and observed, between mind and matter, between self and cosmos, become beautifully blurred when we recognize that all emerge from the same underlying quantum reality. Thank you for joining me on this peaceful journey through the whispering galaxy, where science becomes poetry and the deepest mysteries of physics reveal themselves as love letters from the universe to consciousness. Whether these quantum revelations lull you toward gentle sleep or spark new questions that keep you wonderfully awake, know that you have touched something fundamental about the nature of existence itself. Sweet dreams, fellow quantum travelers, and may you rest knowing that you live in a universe far more interconnected, far more alive with possibility, and far more beautiful than words could ever capture. Until we meet again among the stars and equations, where wonder never sleeps and curiosity never fades.